How are you today? Good. All right, excellent. So, as usual, let's recall what we have learned last week. Last week, we talked about semiconductor, right? And we first realized the differences between metal and semiconductor is that semiconductor has a band gap, right? Okay, and then metal has no band gap. That's why metal has a very good electrical conductivity. And then the applications of the semiconductor, as we know, it can be a transistor, which is the one you use in your computer, in your mobile phone, and anywhere, right? Even your motorbike, right? And then the application not only involve transistors for the semiconductor, but also like solar panel, right? Solar cell, and like LED. That's also the applications. And then after that, we learn the compound semiconductors, which involve band gap engineering. That means you want to change the band gap, you can. You want to design a product which has your desired band gap. Then you can use different type of semiconductor and mix them together. And you can make this kind of semiconductor with a desired band gap. So this is what we call band gap engineering. Okay? And then after that, we learn excitation of a semiconductor. There are three topics. The first topic is photoexcitation, which is the one to measure the band gap of a semiconductor. If you have a semiconductor with an unknown band gap, this is the method you can find out the band gap of the materials. Okay, and the second topic is thermal excitation, and we know that we use thermal energy to change the conductivity of the semiconductor. And as we know, using thermal energy is very difficult to tune the conductivity of the semiconductor, because normally the temperature is too high. So the material will change the phase from solid to liquid. So as a result, it is not really possible, or I should say it is impossible to use thermal excitation to excite the semiconductor. Right, the third one is, which is the most important one, we call chemical excitation. By put the different dopants in the semiconductor, such as silicon, and you can also change the conductivity of the semiconductor. And the case here is that you use boron, or use phosphor, or use sulfur to change the conductivity of the semiconductor. If you use boron and into the silicon, and this is what we call positive or negative. If you put a boron into a silicon, and this type of semiconductor is called positive semiconductor, positive type semiconductor, or negative type semiconductor, and why? Anybody want to tell me? Early bird. 0.5 point? Which one? Boron is P-type or N-type semiconductor? Chinese? Mandarin? Anyone? 0.5? No? Okay. P-type. You know, P-type, can you tell me why? Okay. Okay, P is stand for positive, right? Sorry, P is positive. Thank you. You are right. Okay, P is positive. So boron has a 3 valence electron. So, but compared to silicon has 4 valence electrons. So when you put a boron into a silicon, to make 4 bonds, and you short of 1 electrons. Instead, you have extra electron hole. Okay, so that's hole is not electron. So we say positive. because electron has a negative charge. Okay, but if you put a phosphor into the silicon, that means phosphor has 5 valence electrons compared to silicon, which has a 4 valence electron. So you have an extra electron. So this is what we call negative, right? N-type semiconductor. Okay, thank you. So this is the one we learned last week. Okay, so today we are going to talk about another topic, which is secondary bonding. You know, we have already learned there are 3 types of the chemical bonds. They are, firstly, ionic bond. Secondly, covalent bond. Third, mechanical bonds. These 3 are chemical bonds. And today we are going to learn physical bonds. But before we learn physical bonds, let's look at this topic, which is you have, you know, like water. Water can be ice, which is solid. And then water can be a liquid, right? So the water can, I should say H2O can be a solid. We call it ice. H2O can be a liquid. We call water, right? H2O can be a gas. We call steam or vapor. So this is gas phase. One H2O can be gas phase, liquid phase, and solid phase. And why? Is there any energy like this? Can we talk about this in terms? Can we talk about this in terms of energy? Right. So this is the case of the oxygen. Oxygen can be a solid, which oxygen molecule to H2O means O2, right? They pack very closely, and this is solid. And if you separate this a little bit, then H2O O2 can be a liquid, and you pull the oxygen molecule apart away very far, and this regarded as a gas. So when you take a look of this picture, and you realize the density of the oxygen in solid phase will be greater than the oxygen in the liquid phase, and it will be greater than the oxygen in the gas phase. You know, the definition of density is a gram per, well, here is gram per cubic centimeter, right? So as you know, if the molecules are far away from each other, the density will be low. That's for sure, right? Okay, so the density is like this. And water, as you take a look of the property of the water, it should be the same, right? So the density of the solid need to be the greater the density of the water, and it need to be the higher density of the steam. Generally speaking, yes. But you see that, well, you might say, well, Professor, why water is different? This applied to the general case. Density of solid greater than density of liquid, greater than density of gas in the gas phase. But water is different. Why? Because the density of solid is density of H2O in solid phase. I should say the density of ice is less than the density of the water. Why? We are going to talk about this later, okay? Okay, so let's think of the formation of the gas, liquid, and solid in terms of energy. Okay, so if you think of the ionic bond compounds like NaCl or, you know, sodium chloride or anything, we already learned this is called ionic crystal formation. So you might give me many examples like sodium chloride, magnesium oxide, something like this. This is called ionic bondings. But when you take all the ionic compound together, you think that, well, this is ionic compounds. You might find some of the ionic compound is solid. Mainly, ionic compound is mainly solid. Okay, but however, there are some ionic compounds are in the liquid form. That's why we call ionic liquid. I don't know whether you have heard about this or not. Ionic liquid. Ionic liquid. So this is, so we cannot explain the formation of gas, liquid, or solid using ionic bond compounds. No. How about the covalent bonds, covalent compounds? Okay, you list the covalent compounds like CH4, SF6, CL2, H2O, blah blah blah, and you realize this is in gas form, gas phase. This is liquid. Okay, so this is molecular, right? And how about network? Network means that covalent compound, you put it together in a very dense form. So this can be solid, like what? Like diamond, carbon, graphite, right? So in a covalent bond, you can find covalent compound, you can find some species, some materials in gas phase, some materials in liquid phase, some materials in solid phase. So again, you cannot explain the formation of gas, liquid, or solid using covalent compound. Okay? So how about metals? Again, metal normally, generally speaking, you find metal in solid phase, in solid form, right? However, like mercury is in liquid phase, liquid form. So again, you cannot explain formation of gas, liquid, or solid using metallic bonding. Okay, right. So how can you explain the formation of the gas, liquid, or solid? In this case, we use the cohesive forces against destructive forces. This is in terms of the force. However, if you in terms of energy, you will use the bonding energy versus the thermal energy. We use this way to explain the formation of a gas, liquid, or solid. How? Okay, take a look of this. If we want to put this O2 together closely, that means this interaction needs to be strong, right? So it can be closer and closer. So if the energy is strong, and at least it will be closer. However, if you increase the temperature from this system and increase, and this molecule will be pulled apart, right? If you increase the temperature higher and higher, oxygen, solid oxygen will become liquid oxygen, will become gas oxygen. So that's why we say the thermal energy, the environment energy, thermal energy against what? Against the cohesive energy, the energy between molecules. Okay? So the bonding energy of the substance versus what? The bonding energy of the substance. This is substance, right? The bonding energy between these two molecules, against what? General thermal energy. This energy, if you put this container into an environment which has a 100 Celsius and 1000 Celsius, the formation, the form will be different, right? Okay, again, the ionic crystal, you know, let's make an example using in terms of energy. It's like sodium chloride. The bonding energy of sodium chloride is 8.18 electron volt. So this is very strong. So if you have a sodium chloride crystal, which is salt, right? And against what? Against thermal energy at room temperature, the thermal energy is about 1 out of 40 electron volt. 1/40. So that will be 0.025 electron volt. So if you have this energy against this energy, this is too much difference, right? This is very, very strong. So it doesn't mean you can take sodium and chlorine away using the energy at room temperature. No. But you know, sodium chloride and sodium chloride for example, this is sodium chloride, sodium chloride. Sodium chloride, between sodium chloride, there's some extraction energy. That's a difference. This energy here, this energy is 8.18 electron volt. Okay? But not this energy. Right. How about covalent crystal? Covalent crystal like diamond. You know the band gap is 7.4 electron volt. Again, at room temperature, diamond is in liquid, is in a gas, solid phase, right? A molecular like sulfur fluoride and water. You know, sodium fluoride is in gas phase. This is in gas phase. This is in gas phase, and this has a big. This is a big molecule, and water is a very small molecule. And why water is in the liquid form, and the sulfur fluoride is in gas phase, is in gas form. Why? That's why we are going to talk about this today. So when we talk about this today, we are talking about intermolecular forces. Actually, there are two types of the bondings or force between in the molecule or between molecules. Intramolecular bonding. Intramolecular means what? That treats what is going on inside the molecules, between atoms. So this atom and this atom, there are some bonding energies. That's why we call intramolecular bonding. So I'm sure you know now, we are talking about what? Chemical bondings, like metallic bond, covalent bond, or ionic bond. Okay, this is called intramolecular bonding. And we use electron domain theory to explain this, okay, to explain the shapes of the molecules. So this is what we call primary bonds, and also we call chemical bond. There's chemical bonding here between each other. However, for the intermolecular forces, that's why it become gas, liquid, or solid. We are talking about intermolecular forces between these. So to determine the state of the aggregation, state of aggregation is what? Solid, liquid, or gas. Okay, so this is what we call secondary bonds or physical bonds. Of course, when you think of chemical bond and physical bond, which one will be stronger? Chemical bond or physical bond? Of course, chemical bond, right? This bonding will be much stronger than the bonding between each other, between the molecules. Okay? Right. So there are four types of intermolecular forces. So between here, there are four, actually three types. So this one, now let's move to the sections 2.7, secondary bondings. And van der Waals, or secondary bonding, sometimes we call van der Waals bondings. And the first topic we are going to talk is dipole. The second one is dipole interaction. And there are three types of dipole interaction. The first one is called dipole-dipole interaction. Second one is dipole-induced dipole interaction. The third one is induced dipole interaction. And this topic will be very likely to be in your final exam paper. Okay? So please pay a little bit attention to this topic. Right. So let's go back to the secondary bondings. So the secondary bonding is what we call van der Waals bond or physical bonds, are weakly in comparison to the primary or chemical bonds. Okay, so bonding energy normally is less than 0.1 electron volt per atom. So when you talk about this physical bond, is weaker than the chemical bond. Okay, so secondary bonding exists between the virtually all atoms or molecules. This is molecules, right? It can be atom and between this, but its presence may be obscured if any of these three primary bonds type is present. So this environment, you have chemical bond, you have physical bond. Unless these two molecules are very far away to each other. So there is no physical bond. So inner gases, stable electron configuration, so you can find, normally it's the secondary bond is very weak for the inner gases because of stable electron configuration, stable electron structure. Why? Because we are going to talk about the dipole. Remember, we talked about dipole and polar molecular and non-polar molecular. This is a non-polar molecular, so there is no this is a very stable electron configuration. Okay, so types of the secondary bonds, there are two types. The first one we call the van der Waals bonds. The second one is called the hydrogen bond. Hydrogen bond is a special case of the van der Waals bond. Okay, it's a special case. So basically, if we talk about van der Waals bonds, it involves hydrogen bond. So why you have secondary bond? Because secondary bonding arises from the interaction between dipoles. There are some dipoles here. Okay, so now what is dipole? I hope you still remember, right? This we already have this in your midterm exam. So electrical dipole exists whenever there is some separations of positive and negative portions of electron or molecules. So induced dipole is that this is the atom. Okay, this is the atom, and electron is symmetrically distributed. Excuse me. Nobody want to respond something? If I say excuse me. No, you don't know what happened, right? Bless you, right? Thank you. Okay. Bless me. Induced dipole. So this is a atom. This is atom. And this atom has a symmetrical electron distribution because there's no interaction between atoms. There's no atoms surrounding this atom. Okay? So this is a atom. However, if this atom is closer to some other atoms, they might have some interaction. And this atom may change to like this. The electron cloud might change like this. So this is what we call induced atomic dipole. Okay? So you have positive charge here because you don't have enough electron, and you have more electrons here. So this is called delta minus, delta plus, and this is what we call dipole. However, overall it's neutral. There's no charge, but this part is positive charge. This part is positive charge. This part is negative charge. And we can use this symbol or this symbol to represent an induced or a dipole. Okay. So how can this happen? So this is called polar molecular. Polar molecular, because hydrogen and chlorine become hydrochloride, and you know the chlorine likes electrons, so this electron will be pulled into this one. Why? Because of electron negativity, right? Okay, so this part will have electron deflection, right? This one have enriched electrons in this region, so you have this is dipole. However, because these two are atoms, so this one what we call is polar moleculars. So permanent dipole moments exist in some molecules by virtue of the asymmetrical arrangement. Asymmetrical means what? It's not well distributed in this environment, right? So of the positively and the negatively charged regions. This is positively charged region. This is negatively charged region, right? Okay, such molecules are termed polar molecules. No problem, right? Okay, so this is an example. Hydrochloride molecules is a permanent dipole moment. So this is a polar molecule. So a permanent dipole rises from the positive and the negative charges that are respectively associated with the hydrogen and the chlorine ends of the hydrochloride molecule. Okay? Right. So the secondary bonding forces rise from what? As we know from just now, is atomic dipoles. You have atomic or moleculars, right? Or molecular dipoles. This is water, for example. H2O, right? So this is a polar molecular. This is a polar atom induced polar induced dipole, right? This is the polar molecular. So when there was a bonding between two dipoles, is you have interaction between these two waters, right? So this is chemical bond, this is physical bond, because what? Because you have positive charge region, you have negative charge region, and they will be close, they will be attracted to each other. So the bonding results from the Coulombic attraction, right? Positive charge, negative charge. This is Coulombic attraction. Okay, between the positive end and negative regions of the adjacent one. Okay. Right. So again, positive charge, negative charge, positive charge, and there's an interaction, Coulombic attraction. Okay. Right. So now we want to understand the types of the dipole interaction. There are three types. The first type is called dipole-dipole interaction. The second type, or in this case, is polar molecular. So in your midterm exam, you need to use polar molecular to make an example to explain the dipole-dipole interaction. Okay? The one of the important, well, you can use water as an example to explain dipole-dipole interaction. The second one is called dipole-induced dipole interaction. Okay? This will be, I will give you another example to explain dipole-induced dipole interaction. So you can have a polar molecular as a dipole, right? And you can use another inner gas or non-dipole, non-polar molecular as an induced dipole example. Okay. The third one is induced dipole interaction. And this is a little bit complicated. I'm going to tell you this later. Okay. So induced dipole forces are temporary and fluctuating with time. So this is very important. This is matter of time. Okay. So I'm going to explain this one by one to you. Start from the dipole-dipole interaction. Dipole-dipole interaction normally we also call permanent dipole bonds. So this is, I just give you an example, hydrochloride. If you have a hydrochloride here, and then I hope you still remember, this is positive charge end. This is negative charge region, right? So this is a hydrochloride molecule. And however, if there is another hydrochloride molecule close to this one, and of course you have positive charge, you have negative charge. Okay? And this will attract to each other by Coulombic force. Right? So there's a bond here with the energy. If this energy is stronger than the energy at room temperature, this one will be much closer. If this bond energy is smaller than room temperature, then this will be pulled apart, right? Because of dispersion. Okay, so this is attraction force. So interaction occurred only between polar molecules. So dipole-dipole interaction only occurred between polar molecules. Okay. However, you have a third one and fourth one. They'll get together. You might say, well, Professor, what happens if this is different position? Chlorine here and hydrogen here. Of course, you have a repulsion force, right? So it depends on the energy in the environment. Okay, let's make this as an example. So you have something like this. So you can have a bonding between the molecules, and this is what we call dipole-dipole interaction. Okay, this is a hydrochloride example. So the energy of the dipole-dipole interaction, when we talk about the energy between these two molecules, we are not only talk about this energy, but also we talk about this energy. So let's take a look. So the energy of the dipole-dipole interaction normally is about 5 kJ per mole, which is very weak compared to the chemical bonds. Okay, so the energy is the proportion of the mu, which is mu power 4 divided by R power 3 times the reciprocal of the temperature. So again, you know that the temperature is against the energy. If the temperature high, and this will take out, the energy will be low. This high, this will be low. Okay? How about mu? What is mu? Mu is called dipole moment. R is the interpolar separation. This part. This is called interpolar separation. So this is if you have shorter distance, that means what? The dipole-dipole interaction is high, right? Okay. Okay, if you have high energy, that means this R will be small. Right? This will decrease. Increase this, decrease this. Okay, so mu is what? Mu is the charge, dipole charge times what? Times D. D is what? Dipole separation. This one is this part, dipole separation. If you have a larger separation, you have a stronger energy. Okay? Okay, if D is large, it means that the separation of the dipole, this one separation of the dipole is large, and energy will be large. Okay? You don't need to remember this equation, but you need to know the concepts, especially this distance and the temperature. Okay? So when the temperature is low enough, that means RT stands for room temperature. Room temperature is 10 kJ per mole. Okay? The thermal energy will not disrupt the bonds and are formed by this dipoles interaction. So again, it depends on the thermal energy and the bonding energy. Okay? This high, then this will be liquid, this form will be liquid, this low, and then this will be solid, for example. So hydrochloride is the chemical you might use in laboratory, especially you are students from the chemistry department or chemical engineering department. This is what we call hydrochloride in aqueous phase, in aqueous solution. Okay, aqueous solution. So how do you call this in Mandarin? 盐酸, right? 盐酸. Okay, but this is not the one we are talking now. We are talking about hydrochlorine because this 盐酸 is in water. Okay, so it's different. So for example, if we think of the hydrochloride in gas phase, this is gas phase, right? A gas at room temperature is these two molecules are very far away. That's what we call it. This is in the gas phase. If we decrease the temperature, okay, if we cool down the environment of these molecules, for example, go down to minus 85 Celsius, and these molecules will become liquid phase. So what does that mean? This hydrochloride will be closer to the another one. This is liquid. And again, from the boiling point means what? If the temperature go up to minus 85, this will become gas phase. But if you cool down to the minus 85, this will become liquid. This is what we call boiling point. Right? How about melting point? Melting point means that if we, again, we cool down the temperature down to the minus 115 Celsius, hydrochloride will become hydrochloride in gas in solid phase, in solid form. So the thermal energy is low enough. You know, this is thermal energy. The energy in this environment is low enough that at the temperatures below this value is weak interaction, dipole-dipole domains. So this, because the environment energy is very, very weak, so this energy domain, this situation, so it becomes solid hydrochloride. So this one will even become closer. Right? Okay, so this is, in this case we call the dipole-dipole force is greater than the thermal force, or dipole-dipole energy is greater than the thermal energy. Okay? How about the solution, hydrochloric acid? This is what we call hydrochloric acid, and we use in the laboratory. Okay? It's different. The difference is because this dissociate hydrogen and chlorine associate and become like in the form of this. And chlorine anion is a very strong chemical. Okay? So dipole-dipole interaction is that, of course, you understand there are some attraction, there are some repulsion. So we are talking about this energy against the thermal energy, right? This energy is greater, and this will be molecular will get closer. Okay, so you understand this now? So this is R, this is D. Well, this is not exactly right, but just want to let you know this is the separation between the dipoles. This is the distance between the molecules. Okay? And temperature. Right. So permanent dipole bonds is that the van der Waals forces exist between the adjacent polar molecules. And then the association bonds energy are significantly greater than the bonds involved in induced dipoles. Okay? So this is explanation and this is example. So this is between the molecules, this is between the polymers, a long chains. You know, you have a long chain polymer, and then there's interactions between the atoms. Okay? Right. The second topic is induced dipole interaction. Okay. This dipole molecular and induced dipole bonds. So this is example. The present in a solid. Okay. The present in the solutions of the. Excuse me. The present in the solution of the one polar and the non-polar species. So this is example. Hydrochloride, right? And if assume again you have a negative N, positive N and negative N, and this is for sure this is polar molecular. And however, if something closer to this molecular, for example, like argon is a non-polar species, then what happens? That will be argon will be, the electron around here will be induced, will be pulled apart to this part. If this is closer enough, and this region will become positive, this region will become negative. Okay, this is what we call induced dipole. Induced dipole. So you have electron diffraction zone, and you have a electron rich region. And then what we do is and then again, if you have hydrochlorine here, and it will be this part is positive N, this is negative N. Okay, and again and again. So this is what we call dipole-induced dipole interaction. So in your final exam, please make this example for me, and let me know you understand the concept of the dipole-induced dipole interaction. Give me some simple explanation in Chinese. Okay, you don't need to write in English unless you wish, you want to. Of course, you are welcome to write your explanation in English. So this is the energy is a proportion to the reciprocal of the R. Okay, because there is no separation here. Right, so now we have one question for you is that we call polarization. So the scenario will be the same. This is the hydrochloride and argon, right? So positive N, negative N. However, this is argon, right? So if we put a helium here, of course helium will be induced, and this is positive N and negative N here. So now I want to ask you, which interaction is stronger? This energy will be stronger than this one, or this one will be stronger than this one? Which one? The bonding energy, if I want you to compare. Okay, this is what we call polarization. 极化. The polarization is the electrical charge displacement, and we use alpha to represent electrical polarizability. Okay. So polarizability is the measurement of the ease of the electron displacement. Why this is so important? Because polarization is a proportion. Polarizability is a proportion of electrons, numbers of electrons, and the size. If you have bigger size, that means the separation will be bigger. And then that means that this negative N and negative N and positive N will be, the interaction will be stronger, because these are far away from the center of the nucleus, right? So that's why we say the polarizability, argon will be stronger than the helium. So the bonding of these two molecules, two species, will be stronger than bonding between these two species. Okay, so the measurement of the electrical polarity of a system of the charge is called P. P is equal to alpha. Alpha is the polarizability and times the electrical field. Of course, you don't need to really understand this, but what I want to tell you is that this bonding is stronger than this bonding because of size and the electrons. Okay, so polar molecular and induced dipole bond is like this. If I have argon here and close to hydrochloride, and this is in the beginning this is not an induced dipole. There's no dipole. Okay. However, if it is closer enough, the polar molecule can also induce the dipole in adjacent non-polar molecules or atoms, and a bond will form as a result of attraction forces between two molecules. So this one will be induced. Look at this. It becomes like this, if this is closer enough. So argon will have dipole by inducing by hydrochloride. So this is van der Waals bondings. So the magnitude of this bond will be greater than for the fluctuating induced dipole. So what is fluctuating induced dipole? this is important. So I think now let's have a break to play Kahoot first, and then we will continue to talk about this topic. Okay, it's time to play Kahoot. How to play Kahoot. And one of the reasons I want to play Kahoot is I want you to go home and review what I just told you, and then you can get the right answer in the Kahoot, right? Right, okay, so now we already learned dipole-dipole interaction, dipole-induced dipole interaction, and then next one is induced dipole interaction. Why there's a induced dipole interaction? And sometimes we call this fluctuating induced dipole bonds or fluctuating induced dipole interaction. Why? Let's take a look at an example. Have you heard something like argon ice? Have you? You know, argon, at room temperature, argon is a gas. It's in gas phase, right? And just now we talked about solid hydrochloride. Solid hydrochloride is, that means the molecules of hydrochloride is very, very close together, get together. Okay, and what's going on with this? Because you reduce the temperature, right? And the bonding between these two is stronger than the energy of the environment. That's why these get together. But argon has no dipole. Why? So argon, if you replace this to argon and argon, why argon and argon has an interaction? But this really happened. We can see this in our real life. For example, argon ice, if you decrease the temperature to like 87 Kelvin, it becomes liquid. So you have a liquid argon. And if you reduce further the temperature to the 84 Kelvin and reach to the melting point of the argon, this becomes argon ice. If you see argon ice, yes, if you take argon ice out from 84 Kelvin to the room temperature, it will melt. And this very soon become a vapor or liquid. You have liquid phase argon and gas phase argon. And this is what we call argon ice. Why? Argon is not induced dipole, is not a polar molecule. Why? So we can imagine argon and argon ice, solid argon or argon ice, they are very close to each other. Each atom very close to each other. So they must have an interaction of the energies between argon and argon. And how are you going to explain this? There is no dipole. What bonds argon to argon? So it's not ionic bond. It's not chemical bond anyway. So it's not a primary covalent bonding. It's not a secondary bonding, what we just learned, dipole-dipole interaction or dipole-induced dipole interaction. And there's a gentleman, a scientist, he's a German-born American. He's a Fritz London. He said that, wow, let's call this London dispersion force or induced dipole interaction. So this is induced dipole interaction. So what is this? Is a dominate in non-polar species. So this induced dipole interaction is not only can be seen in the non-polar species like argon, helium, whatever. Methane, for example. So let's take a look of this. Let's take a look of the explanation of this London dispersion force. We use LDF. So electrons are in motion. You know, electrons are always in motion. At time 1, it might be here. Time 2 might be here. Time 3 might be here, electron. Okay? And at a certain moment, like time equal to x, in a certain moment, this will be, you have electron here, so you have electron-rich region, and you have electron depletion region. Right? So at time equal to x, something like this, it can be like this. So at this moment, if the room temperature is not, is the environment energy is very weak, it's very low, the temperature is very, very low. So you will see the energy come out from here because the electrons from the different molecules, atoms, start feeding and avoiding each other, feeding and avoiding each other. The electrons density in the molecules, atoms become redistributed in a proximity to one another. So at time, in a certain moment, this has a delta negative, delta positive. So you, at this moment, this part will be induced to become negative. This part will become positive. Again, this part will become negative. This part will become positive. Okay? Right. So this is frequently described as a formation of the instantaneous dipoles. So by the different time, you have different distribution. So this bonding is very, very weak. Okay, that attract one and each other because these are all induced. So the time fluctuating dipole is a LDF is present in all systems. So this, you can see this in any cases, but because the bonding is very weak, so you always neglect this kind of energy. But this exists, present in all the systems. Okay? So LDF here, I just give an example. Atom to atom, for example, helium, right? Helium at time equal to X at certain moment, this is a negative N, positive N, and this will be induced. So this become negative N and positive N. So induced dipole. How about the molecules? Example molecules is like this hydrogen. Hydrogen is a non-polar molecule. So this bond here and the electron is well distributed in the hydrogen molecule. So at the temperature is low enough, and this one, negative charge, positive charge, this one will be induced. So we have a molecular example for you here. Right. So London dispersion force, LDF, is that intermolecular forces inhibited by non-polar molecules or atoms. So in your final exam, you need to give me an example and to explain what is London dispersion force. Okay, so this is the part of the van der Waals forces, of course. Okay. So this is, again, this is a proportion to the polarity and the distance. So if you have a bigger molecules, the London dispersion force will increase. Okay? So the increased polarity of the molecules with larger and dispersed electron cloud. Of course, you have a lot of electrons, so it's easy to have an induced dipole or dipole, right? Because electrons are very far away from the nucleus if you have a bigger atoms or you have a lot of electrons. So this example to tell you that in a periodical table, at room temperature, which is 1 out of 40 electron volt energy. So fluorine is in gas phase, is in gas form. Chlorine is in gas form, but boron is in liquid phase. Iodine is in liquid phase, is in solid phase. So it's very different. You know, the environment also give you the same energy, but this one, once you have a bigger atoms or molecules, and this one become, and if from gas become liquid to become gas, from the gas become liquid, become solid. Okay, because of the London dispersion force. So larger amount of surface contact, so you have a lot of, because large surface contact, you have the random dispersion forces will be increased. Okay, so greater surface areas means the closer interaction between different molecules. So here just give you an example of iodine crystal. So iodine crystal actually actually iodine crystal is not ionic bonding. It's a covalent bond between two iodine atoms. But because the iodine molecules are very close to each other, so it becomes iodine crystal. So crystal can be formed by ionic bonding, can also be formed by covalent bonding. Okay, because of random dispersion force in this case. So intramolecular is called covalent bond, but intermolecular is fluctuating induced dipole bonds. Again, I want to let you know whatever. This is covalent bond. This is LDF. Right, so you will see a lot of molecules get together, become solid. However, if you put this in the environment, it's easy to vaporize if you increase the temperature. Okay, especially on the surface, the energy is very high. So this energy will be, this molecule will be vaporized. So you can see something like this. Okay, so you might heard that in Jupiter there are some solid methane. Solid methane is the same explanation. You put this methane together, and because temperature is very low, so methane gases will become methane solid. Solid methane. Okay? Right, so the effect of the molecular value on the random dispersion forces we call polarability. Let me see that how much I can go. Right, let me finish this. So this is when you take a look of this example. This is called propane, which you have CH3 at both ends. You have CH3 at both ends, but a different chain length of different chain only. You have CH2, only one CH2. You have 6 CH2. You have 18 CH2. And this is what we call propane, octane, and ecosane. Okay, so this normally we use as a fuel. Okay, and this one we use as a gasoline for your car or for your motorbike. Right, so you use this at home to burn, to cook, right? So the molecular weight here is 44, 114, and 282. So as you know that if you have a higher molecular weight, the boiling point will be high. The melting point will also be high. Why? Because of the random dispersion force, or we call polarizability. So this is in gas. This is in gas phase, gas form at room temperature. This is liquid at room temperature. This is solid at room temperature. Because this is a long chain of the molecule, right? This is short. And we are not talking about, this is one of the examples to tell you that this is molecular weight, this is the boiling point. As we just told you that if you have this is 1 carbon, 2 carbon, 3 carbon, 4 carbon, and go up to 12 carbons. But when we talk about this is a room temperature. Below this line, this is gas at room temperature. This is liquid at room temperature. And we are not talking about if you have more carbon, you will become the liquid, or if you have if you don't have enough carbon, you will become gas. No, we don't talk about this in this way, because normally we think that a higher molecular weight will have a higher boiling point. In this case, or from these figures, it will be easy to understand this way. However, this is not exactly right. When we talk about gas or liquid or solid, we always talk about the polarizability. This is important. Okay, because probability is related to the electrons and size. Remember, electron and size. The size bigger is easier, but this is not only factor we need to consider, but also the probability, the numbers of electrons. So molecular size greater, if you have higher molecular size, then that means your probability is high. And if your probability is high, then you have a higher boiling point. Okay, so solid, liquid, gas, liquid, or solid is about probability. Right. Okay, so that's it. I want to explain to you for the fluctuation dipole. I think I already explained this to you. So this bonding energy might be in the Kahoot next week. So I want you to know that the permanent dipole bonds, dipole interaction, the energy will be greater than what? Than a dipole-induced dipole interaction, and the energy will be greater than what? London dispersion force. Right? Because this is very weak, and this is strongest because you have induced dipole and induced dipole interaction. Okay? So next week, if I want you to choose, if in the Kahoot, if I want you to choose which one is correct or which one is not correct, and this might be one of the answer you want to know. Right. Next topic is hydrogen bond. So I think I'm sorry that I have a visitor from India. So I need to be with him today. So I want to finish our lecture now, and